One of the most debated topics in quantum mechanics is the nature of light. Is it a wave or a particle? But maybe that's the wrong question. In this video, I want to show you the actual calculation revealing that light has a dual nature. You're welcome to get pen and paper and follow along. By the end of this video, you will know exactly how Einstein discovered the wave-particle duality of light. If you know anything about quantum physics, you are aware of the so-called wave-particle duality and the long debates around the nature of light. Just in case you're unfamiliar with the term, wave-particle duality refers to the observation that sometimes light exhibits properties that we associate to waves, whereas under different conditions, we observe light showing properties that we assign to particles. This leads to the obvious question: is light a wave or a particle? In March 1904, an important article was published by a young Albert Einstein under the title "On the General Molecular Theory of Heat." We hear a lot about the articles that Einstein published in the year 1905, but he also wrote some foundational articles before his miracle year. This one in particular presents a new way to estimate Boltzmann constant, but more importantly, it includes a very significant result about statistical energy fluctuations in thermodynamic systems. If that sounds complicated, no worries, I will explain it. Einstein, like many physicists in the early 1900s, was a master of statistical mechanics, one of the most fundamental fields of physics to which he made several contributions. One very important quantity of any physical system is its average energy, that we denote by this. Just in case this has nothing to do with Dirac notation, these brackets are just a symbol to indicate the average of any physical quantity. If you have taken a course in statistics, you probably learned that probability distributions are characterized by some relevant numbers like the mean, variance, and so on. In a more formal approach, these quantities are called the moments of a distribution, which allowed characterizing the key features of the full distribution. Einstein realized that the second moment, or variance, of the distribution of energy in a thermodynamic system can be used to determine its stability. Physicists call this quantity the fluctuation because it measures deviations around the average energy. This is the most remarkable finding by Einstein prior to 1905. Let me show you what Einstein found. The starting point is a physical system with states of energy E in thermal equilibrium with a larger system at temperature T, like a gas inside a volume. The probability of occupation of each state is given by the Boltzmann distribution. So the two average quantities over energy that we need are explicitly given by these ugly expressions, where beta is 1 divided by kT and omega is the density of states with energy E. No worries that there is no need to evaluate these integrals, but we will need them, so I will put them up here. Here is the trick. Let us calculate the derivative of the average energy with respect to beta. Using the definition above, we find that beta appears in the numerator and denominator. So following the rules of the derivative, we get two terms. Now we notice that the first term is just minus the average on the top right, and the second term is just the square of the average energy. And here, without calculating the ugly integrals, we found that the fluctuations are simply given by minus the derivative of the average energy with respect to beta. Here is Einstein's original paper, where he denotes the average by a bar instead of brackets, and instead of beta, he uses temperature. Applying the chain rule to our result, we recover exactly what Einstein wrote, except for the factor 2 kappa. Without knowing any German, it is easy to confirm that the overall constant 2 kappa is just Boltzmann constant. By the way, all papers by Einstein are available in German and English online. The American physicist Josiah Gibbs discovered the same relation in the year 1902, and this result is sometimes referred to as the Einstein-Gibbs fluctuation formula. Apparently Gibbs pointed out that these fluctuations might not be observable. On the contrary, Einstein put the formula to use for solving the problem of Brownian motion, and then moved to other topics until 1908, when he applied this formula to radiation. I made a whole video about blackbody radiation that you can check later. As a quick reminder, in the early years of the last century, there were two formulas describing the behavior of light coming out of hot objects. Wilhelm Wien found a semi-empirical relation that worked well at mid and high frequencies, but failed in the low frequency range. This is a formula for the energy density per unit of frequency according to Wien. For long wavelength or low frequency, Lord Rayleigh and James Jeans combined the statistical mechanics of Boltzmann with the electromagnetic theory of Maxwell to find that the energy density per unit of frequency is given by this simple relation. These two formulas work well in their respective limits, but they are incompatible, and the great challenge was to patch them somehow in the middle. This is what Max Planck was able to do using some very clever methods that I explained in that video. Planck's formula is this, which was literally verified by the experiments of Heinrich Rubens and Ferdinand Krolbaum the day after Planck discovered it. In late 1908, Einstein decided to apply his fluctuation formula discovered during his doctorate to blackbody radiation, and here is what Einstein did. Consider a volume V of enclosed radiation. The energy density per unit of frequency is the mean energy of the light, divided by the volume and the frequency interval delta nu. From here, the average density becomes this. Now we can use the Einstein-Gibbs fluctuation formula to write this general expression for light's energy fluctuations. We will use these two general relations in what follows. At low frequencies, the energy density is given by the Rayleigh-Jeans formula. Let us calculate the derivative with respect to beta. This can be written again in terms of the energy density. Using the definition of energy density, we find this, so that we can finally write the fluctuations in this form. It can be shown that the overall factor corresponds to 1 divided by the number of wave modes, so that the relative fluctuation is given by the inverse of the number of wave modes. I said that this can be shown, but I did not include it here because it's a very long calculation that includes solving the wave equation. In case you're interested, I have written a step-by-step note showing this proof. Check the link in the description below if you want to get the notes. Let us repeat this procedure now for high frequencies, in which case the energy density is given by Wien's formula. We calculate the derivative with respect to beta, which can be written again in terms of the energy density. Using the definition of energy density, we find this, so that we can finally write the fluctuations in this form. Using Wien's formula, Einstein demonstrated in his first 1905 paper that the average energy is given by n times h nu, where n is the number of light quanta and h nu is the energy quantization found by Planck, so that the relative fluctuation reduces to the inverse of the number of light quanta. In modern terms, we call this the number of photons. Einstein knew that his idea of particles of light would not be well received, so he avoided the word particles. He always referred to light quanta instead. Here is a summary of results. The relative fluctuations are given in terms of the number of wave modes at low frequency and in terms of the number of light quanta or photons at high frequency. Note that in the first case, light is treated as a wave, whereas in the second case, we get a result in terms of particles. But these two results are only the limits of a general energy density given by Planck's formula, which is valid for any frequency. I only show you the limit cases as a warm-up and to explicitly show you how the properties of waves and particles appear separately. Now comes the great reveal. Let us repeat the previous steps for Planck's formula. First, we calculate the derivative with respect to beta. You're welcome to check that this last expression can be written in terms of the energy density in this way. Using the definition of energy density, the derivative becomes this. Now we can finally write the fluctuations in this way. These two terms should be familiar to you now. If I divide by the square of the average energy to obtain the relative fluctuation, we find the sum of the inverse of the number of wave modes and light particles. Let this sink in. Under the assumption that Planck's formula is correct, the energy fluctuations of light are given by the energy fluctuations of light waves plus the energy fluctuations of particles of light. This is it. This is the birth of the wave-particle duality. I recall that the first time that I did this calculation a few years back, I was first shocked by its beauty. But then after days of thinking about this, I found it trivially disappointing. Because by construction, Planck's formula has the Rayleigh genes and Wien's formulas as limits. So this result here should not be a surprise after all. But after some extra thought, I realized that this result does not rely in any approximation. It is not just a combination of the two limits of Planck's formula. It uses the exact Planck formula valid for all frequencies. So this is a general result. It is not an approximation. It is an exact result explicitly showing that the energy fluctuations of light are the sum of a wave and particle parts. As I presented in a previous video, when Planck found his now famous formula, he didn't know its physical meaning. After 2 months of deep work, he discovered that the only way to make physical sense of his formula was by imposing a discretization of the energy exchange between the hot material and the radiation. In other words, the price for explaining the Blackbody radiation was to abandon the continuous energy of classical physics and embrace energy quantization. With the result that I just showed you today, Einstein discovered that Planck's distribution also implies that light cannot be treated as a wave or as a particle, but rather as a combination of both. When Einstein proposed particles of light, under the name of light quanta, in March 1905, the physics community completely dismissed the idea. Light was a wave, as derived from Maxwell's equations and demonstrated by experiments, so people simply ignored him. Now, less than 4 years later, Einstein came back with an even more preposterous comeback. The nature of light involves properties of waves and particles. Einstein submitted his paper in January 1909 with the title On the Present Status of the Radiation Problem, in which he concluded, "The current wave theory of radiation is incompatible with this result." Notice that Einstein's first paper on radiation with the hypothesis of light quanta was easily ignored by the physics community because his predictions required technology that did not exist yet. It took over a decade to experimentally confirm Einstein's predictions. Now he was not introducing a new absurd hypothesis. He was only reporting on a consequence of statistical mechanics and Planck's formula. In March, he sent a letter to one of his personal heroes, the Dutch physicist Hendrik Lorentz, and referred to the surprising outcome of the fluctuation of light as the trifling result of years of reflection, to which he followed with, "I have not been able to work my way through to a real understanding of the matter." Lorentz considered Einstein-like quanta a beautiful idea, but he could not accept the particle nature of light. The Assembly of German Natural Scientists took place in September 1909 in Salzburg, in which Einstein gave a lecture describing these results as follows. The undulatory and quantum particle structure simultaneously displayed by radiation according to the Planck formula should not be considered as mutually incompatible. In this lecture, Einstein also presented one of his inventive thought experiments, placing a mirror inside a blackbody cavity, in which the radiation could reflect, transferring momentum to the mirror. From this, he obtained a formula for momentum fluctuations that looks quite similar to the energy fluctuations, but directly leads to what today we call the momentum of a photon, P equals h nu over c, which can be written more suggestively as P equals h over lambda. This is the formula that would later inspire Louis de Broglie to promote Einstein's wave-particle duality to matter. Despite the total rejection of his ideas, the Salzburg lecture made Einstein a respected figure within the physics community. True, nobody accepted his idea, but the physical reasoning and calculations were flawless. In all the calculations done today, we have used a powerful mathematical tool called calculus. This is something that every science and engineering student has to learn during their first years. But thanks to the sponsor of today's video, anybody can learn these concepts in a fun and interactive way. Brilliant is a learning platform that makes it easy to learn anywhere, right on your phone, with fun lessons that you can do whenever you have time. Related to today's video, I totally recommend the course Calculus in a Nutshell, in which you will learn about derivatives, integrals, and how to use them in real life. With thousands of interactive lessons in math, data analysis, programming, and AI, Brilliant helps build your critical thinking skills through problem solving, not memorizing. Visit brilliant.org/JK0 or scan the QR code on the screen. You can also click on the link in the description to try everything Brilliant has to offer for free for a full 30 days. You will also get 20% off an annual premium subscription. Thank you for supporting the channel using my link, and thanks to Brilliant for sponsoring this video. Einstein's challenge to the physics community remained unsolved for many years after 1909. Most people simply dismiss it as a curious result. The hope was that a future theory of quantum mechanics would be able to eliminate this absurd result. In 1911, at the first Solvay conference, people referred to it as the unsolved puzzle or anomaly. Some of the greatest theorists attempted to solve the mystery. Lorentz, Ehrenfest, Debye, they all failed. One of the weak points identified in Einstein's calculation was his assumption of the additivity of entropy. This is the idea in statistical mechanics that the entropy of a system with two parts is equal to the sum of the two entropies. Einstein, like Planck in 1900, considered statistical mechanics and the laws of thermodynamics to be so fundamental that they should hold in quantum physics. But some suggested that there was no way of knowing if the fundamental rules of statistical mechanics would still be valid in the quantum regime. This was the main point of attack to Einstein's wave-particle duality for over a decade. When the Indian physicist Satyendra Nath Bose discovered a novel method to derive Planck's formula in 1924, Einstein immediately borrowed Bose's method to calculate the fluctuations of light. Once again, he obtained the same result. In late 1925, the first modern theory of quantum mechanics, known as matrix mechanics, was established by Max Born, Werner Heisenberg, and Pascual Jordan. This is a work that is barely discussed on videos about quantum mechanics, and I would love to attempt to describe it in a future video. Let me know what you think. Now that they had a new theory for quantum phenomena, they decided to attack the problem of light fluctuations. In fact, one of the sections, written entirely by Jordan, was dedicated to the calculation of light fluctuations, using the new theory of matrix mechanics. The calculation is long and very tedious. The result? Jordan found it to be exactly the same expression published by Einstein 17 years earlier. They concluded, in the end of the article, our findings lead us to expect this additivity of entropy to hold generally. So, is it a wave or a particle? As I said at the beginning, this question is incorrectly formulated. When we ask it like this, we are a priori imposing that the nature of light is either the classical phenomenon that we call waves or the classical view of particles. I came up with a silly analogy. Imagine that you suddenly wake up in the year 1990 with your smartphone in your pocket, and suppose that the only apps that work are your music player and the game Tetris. If you showed this futuristic device to the people in 1990, they might ask you, is this a Walkman or a Game Boy? This is how a physicist feels when asked, is light a wave or a particle? The correct answer is that it's neither, and the person asking the question is a priori trying to set the possible answer in terms of things that are familiar to them. The smartphone, in my hypothetical story, is a totally new device. It can play music, but it's not a Walkman. It has Tetris, but it's not a Game Boy. In the same way, light is not a wave, and light is not a particle. It is a quantum object that has properties similar to what we associate with classical waves, like refraction, interference, diffraction, and polarization, but it is not a classical wave. Similarly, light also manifests properties that we associate to classical particles, like particle collisions in the photoelectric effect and Compton scattering. A more complete understanding of what light really is requires to move to a topic called quantum field theory, but that goes beyond the scope of this video. During his Salzburg lecture, Einstein said the following: "It is therefore my opinion that the next stage in the development of theoretical physics will bring us a theory of light that can be understood as a kind of fusion of the wave and particle theories of light." Jordan showed that the wave-particle duality was here to stay, and the new theory of quantum mechanics proved Einstein right. During the 1920s, physicists had to accept that light, which according to theory and experiment was a wave, could also have particle properties. But what about the other way around? Could matter, known to be made of particles, also show wave properties?